So here's something worth thinking about as you settle in tonight. Right now, somewhere in the world, a machine is looking at a photograph and recognizing a face. Not because anyone told it exactly what a face looks like, not because some programmer sat down and wrote a rule that says a face has two eyes above a nose above a mouth, but because that machine, over the course of seeing millions and millions of images, somehow figured it out on its own. It learned, and the way it learned, the actual mechanism of how it went from knowing absolutely nothing to being able to do something that even a toddler finds effortless. That's one of the most beautiful stories in the history of engineering. It's a story about brains and math and failure and stubbornness and a handful of people who believed in an idea that most of the scientific world thought was a dead end. And honestly, it starts in a place you might not expect. It starts with a question about how you think, not you specifically, but you, the biological you, the human animal lying there right now with roughly 86 billion neurons firing away inside your skull. Back in the early 1940s, that's where this whole thing begins. The world is at war, and two men, a neurophysiologist named Warren McCulloch and a young mathematician named Walter Pitts, are sitting together, probably in some cluttered office at the University of Illinois, trying to answer a question that had been nagging at scientists for decades. How does the brain compute things? Not in some vague philosophical sense, but mechanically, precisely. What is a neuron actually doing when it fires? Now, by the 1940s, scientists already knew the basics of how neurons work. They knew that a neuron is a cell that receives electrical signals from other neurons through these branching input fibers called dendrites. They knew that if enough of those incoming signals add up past a certain threshold, the neuron fires, it sends its own electrical pulse shooting down a long fiber called an axon, which connects to the dendrites of other neurons. And they knew that the connections between neurons aren't all equal. Some connections are strong, some are weak, some are excitatory. They encourage the next neuron to fire, and some are inhibitory. They discourage it. That was the biology. What McCulloch and Pitts did in a paper published in 1943 was strip all of that down to pure logic. They proposed something radical in its simplicity. They said, look, forget the wet chemistry for a moment. A neuron is basically a tiny decision maker. It takes in a bunch of inputs, ones and zeros, on or off. It adds them up, and if the total crosses a threshold, it outputs a 1. Otherwise, it outputs a 0. That's it. That's the model. And they showed, and this is the part that made mathematicians sit up straight, they showed that if you wire enough of these simple little binary units together in the right way, you can compute anything. Anything that logic can express. These networks of idealized neurons were, in principle, as powerful as any computing machine. Think about what that means. They weren't building a computer. They weren't even really building a model of the brain, not an accurate one. What they were doing was drawing a line, a direct mathematical line, between the structure of the brain and the structure of computation. They were saying that thinking, at some fundamental level, is computing, and computing, at some fundamental level, could look like a brain. Now, the McCulloch-Pitts neuron was incredibly simple. Too simple, really. You had to design the network by hand. You had to decide exactly which neurons connected to which, and what the threshold was, and you had to get it all right yourself. There was no learning involved. The network didn't adapt, didn't improve, didn't figure anything out on its own. It just did whatever you wired it to do. It was like a calculator, powerful in its way, but only as clever as the person who designed it. And that's where a truly fascinating character enters the story. His name was Frank Rosenblatt, and he was a psychologist at Cornell, and he was exactly the kind of person who changes the direction of a field. Brilliant, charismatic, maybe a little too confident for his own good, and absolutely consumed by one idea. What if you could build a McCulloch-Pitts-style network that didn't need to be hand-wired? What if it could learn? Rosenblatt was born in 1928 in New Rochelle, New York. He was one of those restless, omnivorous minds. He studied everything from astronomy to psychopharmacology. But by the late 1950s, he'd become fixated on the idea of building a machine that could perceive, not just process data, but actually look at the world and recognize what it was seeing, the way a brain does. And in 1957, he proposed a device he called the Perceptron. Here's how the Perceptron worked, and I want you to really picture this, because it's the seed from which everything else grows. Imagine you have a grid of light sensors, like a very crude camera, maybe 20 by 20 pixels. Each sensor is either on or off, depending on whether light is hitting it. Those sensors are your inputs. Now, each input is connected to an output neuron by a wire, and each wire has a weight, a number that represents how important that particular input is. The output neuron does something very simple. It takes each input, multiplies it by its weight, adds all those products together, and checks whether the total exceeds a threshold. If it does, the neuron fires. It says yes. If not, it says no. So far, this sounds a lot like McCulloch and Pitts, right? But here's Rosenblatt's key insight, the thing that made the Perceptron different. The weights aren't fixed. They change. They learn. Here's how. You show the Perceptron an image, say, the letter A, and you tell it the correct answer. This is an A. The Perceptron makes its guess. If it gets the answer right, great. You leave the weights alone. But if it gets the answer wrong, say it fails to recognize the A, you go through and adjust the weights. You make the weights on the inputs that were active a little bit stronger, nudging the system so that next time it sees a similar pattern, it'll be more likely to fire. And if it fires when it shouldn't have, if it sees a B and incorrectly says, yes, that's an A, you do the opposite. You weaken the weights on the active inputs, making it less trigger-happy for that pattern. That's it. That's the learning rule. It's almost absurdly simple. You show it examples, you tell it when it's right and when it's wrong, and you nudge the weights a tiny bit each time. And the remarkable thing, the thing that made Rosenblatt famous, is that it works. Given enough examples, the Perceptron converges. It finds a set of weights that correctly classifies the training data. And this isn't just an empirical observation. Rosenblatt and others proved it mathematically. It's called the Perceptron convergence theorem. If a solution exists, if there's some set of weights that can correctly separate the two categories, the learning rule is guaranteed to find it. The year was 1958 when the Navy publicly demonstrated the Mark I Perceptron, a physical machine built at the Cornell Aeronautical Laboratory. It was enormous by today's standards, a room-sized contraption with 400 photocells wired up to a bank of potentiometers, which were basically adjustable resistors that physically represented the weights. When the machine learned, electric motors would actually turn the potentiometer knobs, physically adjusting the resistance, physically changing the weights. It's a wonderful image. A machine literally, mechanically learning, one knob turn at a time. The press went absolutely wild. The New York Times ran a story saying the Navy had built the embryo of a computer that would eventually be able to walk, talk, see, write, reproduce itself, and be conscious of its existence, which, and I love this, is maybe the first, but certainly not the last time that the media would dramatically overstate what neural networks could do. Rosenblatt himself wasn't much help in managing expectations. He was a showman, and he made grand predictions about machines that would recognize people, translate languages, and exhibit creativity. And for a few years, the excitement was real. Funding poured in. Researchers around the world started building Perceptron-like systems. The idea that machines could learn from examples rather than being explicitly programmed felt genuinely revolutionary. Because think about what traditional programming looks like. You sit down and you write rules. If this, then that. You have to anticipate every situation, every edge case, every possible input. But with a perceptron, you just show it examples and let it figure out the rules on its own. The knowledge isn't in the program. It's in the weights. It's distributed across all those little connections, encoded in a way that no human explicitly designed. But here's the thing. The perceptron had a problem. A deep, fundamental problem that would eventually bring the whole field crashing down. And it's a problem worth understanding, because it illuminates something really important about what it means for a machine to learn. The perceptron can only learn things that are, and this is a technical term, linearly separable. Let me explain what that means with an analogy. Imagine you have a table, and on the table you've scattered a bunch of red marbles and blue marbles. Now imagine you can place a single straight stick on the table, and you need to position it so that all the red marbles are on one side and all the blue marbles are on the other. If you can do that, if one straight line can perfectly divide the reds from the blues, then the problem is linearly separable, and the perceptron can learn it. But if the marbles are mixed up in a way that no single straight line can separate them, maybe the red ones form a circle in the middle with the blue ones around the outside, then the perceptron is stuck. It will never find the right weights, because the right weights don't exist. Not for a single layer perceptron. Now, in 2 dimensions, with marbles on a table, this might seem like a minor limitation. But in the real world, most interesting problems aren't linearly separable. Most of the things we want a machine to recognize, faces, speech, handwriting, disease, fraud, involve complex, tangled, overlapping patterns where no single straight cut through the data will do the job. And 2 people saw this with devastating clarity. Their names were Marvin Minsky and Seymour Papert, and they were at MIT. And in 1969, they published a book called Perceptrons that would reshape the entire field. Minsky was already one of the most influential figures in artificial intelligence. He'd actually been a classmate of Rosenblatt's at the Bronx High School of Science, which is one of those coincidences that feels almost too perfect. These 2 men, who'd known each other since they were teenagers, ended up on opposite sides of one of the most consequential intellectual battles in the history of computing. What Minsky and Papert did in their book was rigorous and, in some ways, merciless. They took the perceptron and mathematically proved its limitations. They showed that a single-layer perceptron couldn't even learn something as simple as the XOR function, exclusive OR. XOR is about as basic as logic gets. You have 2 inputs, each either 0 or 1. The output should be 1 if exactly one of the inputs is 1, and 0 otherwise. That's it. And the perceptron can't do it. Minsky and Papert proved it can't, and they proved it elegantly. Now, here's where the story gets complicated and a little sad. Minsky and Papert knew, and they said in the book, that multi-layer networks with additional layers of neurons between the inputs and the outputs, could in principle solve these problems. They acknowledged that. But they also expressed deep skepticism that anyone would find an effective way to train such networks. How would you adjust the weights in those hidden middle layers? The Perceptron learning rule only worked for the output layer because you could directly compare the output to the correct answer and adjust accordingly. But the neurons in the middle, the hidden neurons, how would you know which ones were responsible for an error? How would you assign blame? This was called the credit assignment problem, and in 1969, nobody had a good answer. The impact of Minsky and Papert's book was enormous, and it went far beyond what the mathematics strictly justified. The book didn't just say single-layer perceptrons have limitations. The message that the field heard, the message that funding agencies heard, that department chairs heard, that young researchers trying to decide what to work on heard, was that neural networks were a dead end. The whole approach was flawed. Go work on something else. And that's largely what happened. Funding for neural network research dried up almost overnight. The period that followed, roughly 1969 through the early 1980s, is sometimes called the first AI winter, at least for neural networks. Rosenblatt himself didn't live to see the revival. He died in 1971, on his 43rd birthday, in a boating accident on Chesapeake Bay. It's one of those details that just sits with you. This passionate, ambitious man who genuinely believed that machines could learn to see and think, gone before the world caught up to what he'd started. But the idea didn't die with him. That's the thing about good ideas in science and engineering. You can defund them. You can ridicule them. You can publish a famous book explaining why they'll never work. But if there's something real there, someone, somewhere, will keep pulling on the thread. And during those quiet years, while most of the AI world was focused on symbolic approaches, expert systems, logical reasoning, handcrafted rules, a small, stubborn handful of researchers kept working on networks that learn. They kept asking that question that Minsky and Papert had posed as a challenge. How do you train the hidden layers? How do you teach a network that's more than one layer deep? And the answer, when it finally came together, turned out to be one of the most elegant ideas in all of applied mathematics. It has a name you've probably heard, even if you're not sure exactly what it means. It's called backpropagation, and the story of how it was discovered, or really, how it was discovered and forgotten and rediscovered and ignored and then finally, decades later, changed everything. That story is one of those tangled, beautiful messes that tells you a lot about how science actually works. Not in clean, straight lines, but in fits and starts, with multiple people stumbling onto the same truth from completely different directions, often without knowing about each other. So let's talk about it. The core idea behind backpropagation is, at its heart, a calculus trick. And I know, calculus, late at night, maybe not what you signed up for. But stay with me, because the intuition is actually gorgeous, and you don't need to do any math to feel why it works. You just need to think about blame. Imagine you have a network. Not a single-layer perceptron like Rosenblatt's, but something deeper, an input layer, then a hidden layer of neurons in the middle, then an output layer. You feed in some data. The signals propagate forward through the network. Each neuron does its little weighted sum plus threshold thing, and eventually you get an output, an answer. And let's say that answer is wrong. The network was supposed to say cat, and it said toaster. Okay, so there's an error. You can measure exactly how wrong the output is. That's straightforward. But here's the question that haunted everyone for years. Whose fault is it? Think about it. The output neuron gave a bad answer, sure, but the output neuron was just responding to the signals it received from the hidden layer, and the hidden neurons were responding to the signals they received from the input. The error you can see is at the end of the chain, but the weights that caused the error could be anywhere in the network. It's like, imagine a company makes a terrible product. The CEO announces it, so the CEO looks bad. But maybe the real problem was a bad decision by a middle manager 3 levels down, or a miscommunication between 2 departments, or a flawed assumption made by an engineer in the basement who never talks to anyone. The mistake is visible at the top, but the cause is buried deep in the organization. That's the credit assignment problem. That's what kept people stuck for over a decade. And backpropagation solves it by doing something clever. It works backwards. It starts at the output, where the error is obvious, and then it asks, okay, how much did each connection leading into this output neuron contribute to this error? You can calculate that using calculus, specifically using the chain rule of derivatives. And once you know how much each connection into the output contributed, you can take one step back and ask the same question about the hidden layer. How much did each connection into each hidden neuron contribute to the error that flowed through it? And you just keep going, layer by layer, propagating the error signal backward through the network. Back-propagation. Back-propagation of errors. That's literally what the name means. And here's what's beautiful about it. Once you know how much each individual weight contributed to the overall error, you know which direction to nudge that weight to make the error a little smaller. You're essentially rolling downhill on a landscape of errors, trying to find the lowest valley, the set of weights that produces the least wrong answers across all your training examples. Each tiny adjustment to each weight is a small step downhill. Do it thousands of times, millions of times, and the network gradually learns. Now, who figured this out? This is where the history gets wonderfully complicated. The mathematical foundations, the chain rule, gradient descent, the idea of computing derivatives through composed functions. That's old. That goes back centuries, really. But the specific application to neural networks, the idea of using the chain rule to train multi-layer networks by propagating error signals backward, that was independently discovered by multiple people across multiple decades. The earliest clear formulation is usually credited to Seppo Linnanmaa, a Finnish master's student who in 1970, just a year after Minsky and Pappert's book came out, described the general method of automatic differentiation in reverse mode. That's essentially the mathematical backbone of backpropagation. But Linnanmaa wasn't thinking about neural networks specifically. He was thinking about computing derivatives efficiently in general programs. It was a contribution to numerical methods, published in Finnish, and it went largely unnoticed by the neural network community. Then, in 1974, Paul Werbos, a Harvard PhD student, described backpropagation explicitly as a method for training neural networks in his doctoral thesis. This is remarkable. While the rest of the AI world was celebrating the death of neural networks, this graduate student was quietly writing down the solution to the exact problem everyone said was unsolvable. But here's the thing about PhD theses. Almost nobody reads them. Werbos published papers about it later, in 1982, but by then, the AI mainstream was deeply invested in symbolic approaches, expert systems, rule-based reasoning. Neural networks were yesterday's news. Nobody was paying attention. And meanwhile, in 1982, halfway around the world, David Parker independently rediscovered the technique. And in 1985, Yann LeCun in France derived a similar approach. Multiple smart people, working independently, kept arriving at the same answer. That's usually a sign that the answer is right. When the mathematics is so natural that anyone who looks at the problem long enough will find the same path through it. But the moment that truly changed everything, the publication that finally broke through the noise and made the world pay attention, came in 1986. David Rumelhart, Geoffrey Hinton, and Ronald Williams published a paper in the journal Nature, one of the most prestigious scientific journals in the world, titled Learning Representations by Back-Propagating Errors. And this paper did something that all the previous work hadn't quite managed. It demonstrated, clearly and convincingly, that backpropagation actually worked. Not just in theory, not just on toy problems. It showed that multi-layer networks trained with backpropagation could learn internal representations, that the hidden layers would spontaneously organize themselves to capture meaningful features of the input data without anyone telling them what features to look for. That's worth pausing on because it's genuinely profound. Remember, the whole problem with Rosenblatt's Perceptron was that it couldn't handle problems that weren't linearly separable. It couldn't learn XOR. It couldn't draw curved decision boundaries. It couldn't deal with the messy, overlapping, tangled patterns that real-world data is full of. Everyone knew, in principle, that adding hidden layers could solve this. A multi-layer network is theoretically powerful enough to learn almost anything, but the question was always, how do you train it? And now, finally, there was an answer. You train it with backpropagation. You let the error signal flow backward through the network, adjusting every weight, and the hidden layers figure out on their own what features matter. Think about what that means. You don't have to tell the network what to look for. You don't have to hand engineer features. You just show it examples. Here's an input. Here's what the correct output should be. And the network discovers the relevant patterns by itself. The hidden neurons become feature detectors, and the features they detect are whatever features are most useful for reducing the error. It's learning in the deepest sense of the word. Geoffrey Hinton, one of the 3 authors of that 1986 paper, is someone you should know about, because his story is woven through almost everything that happens next in this field. He's a British-Canadian computer scientist, born in London in 1947, and he comes from a family of remarkable people. He's a great-great-grandson of George Boole, the mathematician who invented Boolean algebra, which is the logical foundation of all digital computing. So there's this beautiful thread connecting the very foundations of computer logic to the man who would do more than perhaps anyone else to make computers learn. Hinton was drawn to the idea of neural networks early in his career, at a time when that was a genuinely risky thing to be interested in. Through the late 1970s and into the 1980s, working on neural networks was a career risk. Funding agencies didn't want to hear about it. Reviewers were skeptical. The shadow of Minsky and Papert's critique still hung over everything. But Hinton kept at it, partly because he had a deep intuition that the brain's approach to computation, massively parallel, distributed, learned rather than programmed, was fundamentally more powerful than the symbolic approach that dominated AI at the time. He wasn't alone in this belief, but he was unusually persistent about it. The 1986 Nature paper was a turning point, but it didn't immediately solve everything. What it did was reopen the door. Suddenly, neural networks were respectable again. Funding started to flow back. Researchers who'd been quietly working on connectionist models, that was the polite term for neural network research during the years when neural network was almost a dirty word in AI circles. Those researchers could finally publish in mainstream venues and get taken seriously. And the results started coming. Through the late 1980s and into the 1990s, backpropagation-trained neural networks were applied to an astonishing range of problems. One of the most famous early successes was Yann LeCun's work at Bell Labs on handwritten digit recognition. LeCun, who'd independently worked out backpropagation in France before joining the American research scene, built a system called LeNet that could read handwritten zip codes on envelopes. This wasn't a toy demo. The United States Postal Service actually deployed this technology. By the mid-1990s, neural networks were reading a substantial fraction of all the handwritten checks processed in the United States. Every time you wrote a check, if you're old enough to remember writing checks, there was a decent chance a neural network was the thing that read the amount and routed your money. That's the kind of practical, unglamorous, world-changing application that doesn't make headlines, but quietly reshapes how civilization operates. LeCun's networks introduced something important that we should talk about, because it shows up everywhere in modern AI. His networks weren't just generic layers of fully connected neurons. They had a specific architecture designed to take advantage of the structure of images. He used something called convolutional layers. Layers where each neuron only looks at a small patch of the input image, and the same set of weights is reused across the entire image. The idea is elegant. If you're looking for, say, a horizontal edge in an image, that edge could appear anywhere. You don't need a separate edge detector for every possible position. You need one edge detector that slides across the whole image, checking each little patch. That's what a convolutional layer does. It's a weight-sharing scheme that dramatically reduces the number of parameters the network needs to learn, and it bakes in a useful assumption that the same kinds of features can appear anywhere in the image. This idea of designing the network architecture to match the structure of the problem, that turns out to be one of the most important insights in the whole field. A neural network isn't just a black box you throw data into. The architecture matters. The way you connect the neurons, which neurons share weights, how information flows through the system. These design choices encode your assumptions about the problem, and good assumptions make learning vastly more efficient. But even with backpropagation and clever architectures like LeCun's convolutional networks, there were limits. And by the mid-1990s, those limits were starting to become painfully clear. The networks that worked well, the ones that could read digits and recognize simple patterns, were relatively shallow. 2 layers, maybe 3. And when researchers tried to make them deeper, to stack more and more hidden layers to capture more complex patterns, something frustrating happened. The learning process broke down. The networks would train incredibly slowly, or they'd get stuck, or the lower layers, the ones closest to the input, would barely learn at all while the upper layers did all the work. There was a specific technical reason for this, and it has a name that tells you exactly what's going on. It's called the vanishing gradient problem, and understanding it requires you to think about what backpropagation is actually doing, mathematically, as it sends that blame signal backward through the network. So picture a deep network. Say it has 10 hidden layers, which by modern standards is actually pretty modest, but in the early 1990s, that was ambitious. You feed in an input, it flows forward through all 10 layers, and out comes some prediction. The prediction is wrong. There's an error. Backpropagation kicks in and starts sending that error signal backward, layer by layer, adjusting weights as it goes. But here's the thing. At each layer, the error signal gets multiplied by certain numbers. Specifically, it gets multiplied by the derivatives of the activation functions at each neuron it passes through. And the activation function that everyone was using at the time was something called a sigmoid. You might have heard of it. It's that S-shaped curve that squashes any input into a value between 0 and 1. It's smooth, it's differentiable, it has a nice biological interpretation. It was the default choice for decades. But the sigmoid has a property that becomes a serious problem in deep networks. Its derivative, the slope of that S-curve, is always less than 1. In fact, the maximum value of the sigmoid's derivative is 0.25, and it's only that high right in the middle. For most inputs, the derivative is much smaller. So every time the error signal passes backward through a layer, it gets multiplied by a number that's at most a quarter and usually much less. Think about what happens when you multiply a number by 0.25, then multiply the result by 0.25 again, then again, then again, 10 times over. You're basically raising 0.25 to the 10th power. That's roughly 0.00000095. The signal has effectively vanished. It's been multiplied into oblivion. And that's exactly what was happening inside deep networks. The gradient, that crucial signal that tells each weight how to adjust, was enormous at the top layers, near the output, and essentially zero at the bottom layers, near the input. The bottom layers couldn't learn. They were essentially frozen, stuck with their random initial weights, because the error signal that was supposed to guide them had evaporated by the time it reached them. And the tragedy of this is that the bottom layers are the ones that need to learn the most fundamental features. In an image recognition task, those early layers should be learning to detect edges and corners and simple textures, the building blocks that higher layers combine into more complex patterns. If the bottom layers can't learn, the whole network is crippled. Now, you might think, okay, just use a different activation function, something with a bigger derivative. And you'd be on the right track, but in the 1990s, that solution wasn't obvious. The sigmoid felt natural. It was inspired by biology. It had nice mathematical properties, and people had built a lot of theory around it. The idea of just swapping it out for something else wasn't the first thing anyone tried. What people tried instead was, well, mostly giving up on deep networks. And this is where the story gets a bit melancholy, because the mid-1990s through the mid-2000s were a second winter for neural networks. Not as harsh as the first one after Minsky and Papert's book, but a real chill nonetheless. The machine learning community largely moved on to other methods. Support vector machines became the hot technique. They had strong theoretical guarantees. They worked well on many problems, and they didn't have this maddening gradient problem. Decision trees, random, forests, kernel methods, these were the tools that got funded, got published, got used in industry. Neural networks were seen as yesterday's technology. Finicky, hard to train, theoretically suspect, and worst of all, they didn't scale to deep architectures. And here's where Geoffrey Hinton shows up again. Because while most of the field moved on, Hinton didn't. He stayed in Toronto, he kept working on neural networks, and he kept a small community of believers together through what he later called the wilderness years. There's something genuinely admirable about this. Hinton had tenure, which helped. He couldn't be fired for working on unfashionable problems. But it still took real conviction to keep pushing when the mainstream of your field thought you were wasting your time. Funding was hard to get. Top conferences were skeptical of neural network papers. Students who wanted to work on neural networks were warned it was a career dead end. But Hinton had a deep intuition that the brain does something like deep learning, that the hierarchical structure of neural processing in biological brains was a clue that deep networks were the right approach, and that the vanishing gradient problem was a technical obstacle, not a fundamental barrier. He just needed to find a way around it. And in 2006, he did something clever. He published a paper that introduced a technique called greedy layer-wise pre-training, and it's a beautiful idea in its indirectness. Instead of trying to train a deep network all at once with backpropagation, which would run into the vanishing gradient problem, you train it one layer at a time, from the bottom up. You take the first layer and train it as an unsupervised model called a restricted Boltzmann machine, which learns to capture statistical patterns in the raw input data. Once that layer is trained, you freeze it and use its output as the input to the next layer. You train that second layer the same way, and so on, building up the network layer by layer, each one learning increasingly abstract features. Only after all the layers have been pre-trained this way do you add an output layer and do a final round of supervised backpropagation to fine-tune the whole thing. And here's what's really clever about this. By the time you do that final backpropagation pass, the weights aren't random anymore. They've been initialized to sensible values by the pre-training process. The network is already in a good neighborhood of the solution space, so backpropagation doesn't have to move the weights very far, which means the vanishing gradient problem is much less severe. You're not asking backpropagation to train the whole network from scratch. You're asking it to make small adjustments to an already reasonable set of weights. The 2006 paper, published in the journal Neural Computation, showed that this approach could successfully train networks with many layers, deeper than anything that had worked before. Hinton called these deep belief networks, and the paper is often cited as the beginning of the deep learning revolution. Which is a bit funny, because the specific technique of greedy pre-training turned out to be a stepping stone rather than the final solution. Within a few years, people found simpler ways to train deep networks directly. But what Hinton's paper really did was change the conversation. It proved that deep networks could work. It gave the community permission to take them seriously again. It was a proof of concept that reopened a door everyone thought was permanently closed. And then things started moving fast. Between 2006 and 2012, a series of advances came together that transformed deep learning from a niche academic interest into the dominant paradigm of artificial intelligence. And these advances came from several directions at once, which is part of what makes this period so exciting. Let's talk about the activation function fix, because it's so simple it's almost embarrassing. In 2010 and 2011, several researchers, including Yoshua Bengio's group in Montreal and others, showed that you could largely solve the vanishing gradient problem by using a different activation function called a rectified linear unit, or ReLU. And ReLU is absurdly simple. For any input, if it's positive, you just pass it through unchanged. If it's negative, you output 0. That's it. No fancy S-curve, no squashing, nothing elegant about it at all. It looks like a bent line, flat at 0 for negative inputs, then a straight diagonal line going up for positive inputs. But here's why it works so beautifully. The derivative of ReLU for positive inputs is just 1. Not 0.25, not some tiny fraction, just 1. So when the gradient flows backward through a layer with ReLU activations, it doesn't get shrunk. It passes through at full strength. Stack 10 layers, 20 layers, 100 layers. As long as the neurons are in their active region, the gradient flows cleanly all the way back to the first layer. The vanishing gradient problem doesn't disappear entirely, but it becomes dramatically less severe. And this is one of those moments in engineering history that makes you shake your head a little, because ReLU was not a new idea. It had been around in various forms for decades. People had used it in different contexts, but nobody had really championed it as the default activation function for deep networks because it seemed too crude, too simple, not mathematical enough. The sigmoid was elegant. ReLU was a bent line. Sometimes the right answer is the inelegant one. So now you have a way to train deep networks, really deep networks, using straightforward backpropagation with ReLU activations, without the gradient vanishing into nothing. But training deep networks requires something else, something that had been quietly growing in the background while the algorithmic breakthroughs were happening. You need computational power, a lot of it. And this is where an unlikely hero enters the story. The graphics processing unit, the GPU, originally designed to render video game graphics, to calculate the color of millions of pixels 60 times per second. And if you think about what that involves, it's basically doing the same simple mathematical operation. Multiply some numbers, add them up, millions of times in parallel, which is, if you squint at it, exactly what training a neural network requires. Each neuron computes a weighted sum. You have millions of neurons. You need to do this computation over and over for millions of training examples. It's massively parallel arithmetic. A researcher at Stanford named Andrew Ng, along with his students, was among the first to really push the idea of training neural networks on GPUs, publishing work around 2009 showing dramatic speed-ups. But it was a group in Switzerland, Dan Sirisan and his colleagues working with Jürgen Schmidhuber, who demonstrated some of the earliest GPU-trained deep networks achieving competitive results on image recognition benchmarks. And the speed-ups were staggering. Computations that took weeks on traditional CPUs could be done in hours on GPUs. This wasn't a marginal improvement. It was a qualitative shift. Problems that were previously intractable because of sheer computation time suddenly became feasible. And all of these threads, the algorithmic insight of deeper architectures, the ReLU activation function, the raw computational power of GPUs, and one more ingredient we haven't talked about yet, were about to converge in a single dramatic moment. A competition. An annual benchmark called the ImageNet Large-Scale Visual Recognition Challenge, where teams from around the world competed to build the best image classification system. The dataset was enormous, over 1 million labeled images sorted into 1,000 categories: dogs, cats, cars, mushrooms, saxophones, everything you can think of. And the best systems in 2010 and 2011, using traditional computer vision techniques, hand-designed feature extractors, support vector machines, carefully engineered pipelines, were achieving top 5 error rates around 25 or 26%, meaning that if you let the system make 5 guesses about what was in an image, it got all 5 wrong about a quarter of the time. Then, in 2012, a team from Toronto entered. Jeffrey Hinton and 2 of his graduate students, Alex Krzyzewski and Ilya Sutskever. Their system was called AlexNet, and it was a deep, convolutional neural network. And it didn't just win. It obliterated the competition. AlexNet achieved a top 5 error rate of about 15.3%. The runner-up that year was sitting around 26%. So think about that gap for a second. In a field where progress usually meant shaving off a fraction of a percent each year, where teams of researchers would spend months engineering slightly better feature detectors to eke out a tiny improvement, AlexNet didn't just beat the competition. It cut the error rate nearly in half. It was like showing up to a track meet and running the 100 meters 2 seconds faster than everyone else. People in the computer vision community didn't know what to make of it at first. Some were skeptical. Some were genuinely stunned. And a few, the ones who had been paying attention to what Hinton's group had been doing for years, felt a kind of vindication that had been decades in the making. Let's talk about what AlexNet actually was, because the architecture itself tells you a lot about why it worked. It had 8 layers, 5 convolutional layers, followed by 3 fully connected layers. By today's standards, that's almost quaint. But in 2012, it was considered deep. And it used several of the ingredients we've been talking about. ReLU activations instead of sigmoids, so the gradients could flow properly through all those layers without vanishing into nothing. GPU training. Krzyzewski split the network across 2 NVIDIA GTX 580 graphics cards, each with 3 gigabytes of memory, because a single GPU didn't have enough memory to hold the whole model. The training took about 5 or 6 days on those 2 GPUs, and it used a technique called dropout, which is worth pausing on because it's such a beautifully simple idea. Here's the problem dropout solves. When you train a neural network, especially a big one with millions of parameters, there's a real danger that the network will memorize the training data instead of learning general patterns. This is called overfitting, and it's one of the oldest headaches in machine learning. Your network performs amazingly on the images it's seen during training, but show it a new image it hasn't encountered before, and it falls apart. It hasn't learned what a dog looks like. It's memorized the specific dogs in the training set. So Hinton and his students came up with this trick. During training, at each step, you randomly turn off a fraction of the neurons. Just set them to 0. Ignore them. Typically about half of them. It sounds destructive, right? Like you're sabotaging your own network. But here's what's clever about it. By randomly dropping neurons, you force the network to not rely on any single neuron or any specific combination of neurons too much. Every neuron has to learn to be useful in many different contexts because it never knows which of its neighbors will be present on any given training step. It's like training a soccer team by randomly benching different players each practice. Every remaining player has to learn to cover more positions, to be more versatile. The team becomes more robust. And when you stop dropping neurons at test time, when you use the full network, all those redundant, robust features combine, and you get better generalization. Dropout was published by Hinton and his students, including Nitish Srivastava, in a 2014 paper, though they'd been using it in AlexNet 2 years earlier. Now, the ImageNet result in 2012 wasn't just a win in a competition. It was a turning point for the entire field of artificial intelligence. And I don't say that lightly. Within a year or two, virtually every competitive entry in ImageNet was a deep neural network. The traditional computer vision pipeline, those carefully hand-engineered feature extractors that researchers had spent decades perfecting, was essentially abandoned. Not gradually, almost overnight. And the impact rippled far beyond image recognition. Researchers in natural language processing, speech recognition, robotics, medical imaging, game playing, they all started asking the same question. If deep learning works this well for images, what happens if we try it on our problems? And this is where the story starts accelerating in a way that's almost hard to keep up with. Because after AlexNet, the improvements came fast. In 2014, a network called VGGNet, developed by Karen Simonian and Andrew Zisserman at Oxford, showed that you could push accuracy further just by making the network deeper, 16 or 19 layers, while keeping the individual convolutional filters very small, just 3 by 3 pixels. The insight was that stacking many small filters gives you the same effective field of view as fewer large filters, but with more non-linear transformations in between, which means the network can learn more complex features. And it uses fewer parameters. That same year, Google's GoogleNet, also called Inception, went even further with 22 layers and introduced these clever Inception modules that processed the input at multiple scales simultaneously, using different filter sizes in parallel and then concatenating the results. It won ImageNet 2014 with a top 5 error rate of about 6.7%. Remember, this was 26% just 3 years earlier. But here's where something really interesting happens, and it connects back to that vanishing gradient problem we talked about earlier. As networks got deeper, 20 layers, 30 layers, 50 layers, researchers started hitting a wall again. Not exactly the same wall as before. ReLU had solved the worst of the vanishing gradient problem, but a new, subtler issue emerged. Very deep networks were actually performing worse than shallower ones, even on the training data. Which is strange, right? A deeper network should be at least as good as a shallower one, because in theory, it could just learn to copy the shallower network's behavior and use the extra layers as identity functions. Layers that just pass the input through unchanged. But in practice, the optimization landscape was so complicated that the training process couldn't find these solutions. The network was struggling to learn even simple identity mappings through all those layers. And this is where a researcher named Kaiming He, working at Microsoft Research, had an idea that was almost embarrassingly simple. What if, instead of asking each layer to learn the complete transformation from input to output, you asked it to learn only the difference, the residual, between the input and the desired output, and then you just added the input back in at the end. So you'd have these shortcut connections, sometimes called skip connections, that let the input bypass a layer or two and get added directly to the output. If the layer didn't need to do anything, it could just learn to output zeros, and the input would pass through unchanged. That's much easier to learn than a full identity mapping. This was the core idea behind ResNet, the residual network, which he and his colleagues published in 2015. And it worked spectacularly. They trained networks with 152 layers, 152. And they won ImageNet 2015 with a top 5 error rate of about 3.6%, which was actually better than the average human performance on that particular benchmark. Let that sink in. A machine learning system, looking at photographs and trying to identify what's in them, was now making fewer mistakes than a person would. And those skip connections, they're such a beautiful piece of engineering intuition. They essentially give the gradient a highway to travel back through the network during backpropagation. Instead of having to pass through dozens of layers of transformations, each one potentially shrinking the signal, the gradient can take the shortcut connections and flow directly to earlier layers. It's like building express lanes on a highway. The local traffic still uses the regular lanes, but the long-distance traffic can bypass the congestion. And this architectural trick turned out to be useful far beyond image recognition. Skip connections show up everywhere in modern deep learning, in the networks that generate images in the networks that translate languages, in the networks that fold proteins. It's one of those ideas that seems obvious in retrospect, but required real insight to formalize and validate. Now, while all of this was happening in the world of convolutional networks and image recognition, there was a parallel story unfolding in a completely different domain: language, text. The problem of getting neural networks to understand and generate sequences of words. And this required a fundamentally different kind of architecture, because language has a property that images don't, at least not in the same way. Language is sequential. The meaning of a word depends on the words that came before it, and sometimes on the words that come after it. The word bank means something different in riverbank than in bank account. The pronoun it in a sentence might refer to something mentioned 3 sentences ago. Language has this long-range dependency structure that's incredibly difficult to capture. The earliest attempts to handle sequences with neural networks used something called a recurrent neural network, or RNN, and the idea is intuitive. Instead of processing an input all at once, like a convolutional network does with an image, a recurrent network processes one element at a time, one word at a time, say, and maintains a hidden state that gets updated at each step. Think of it like reading a book one word at a time and keeping a running summary in your head. Each new word you read gets combined with your current mental summary to produce an updated summary. By the time you reach the end of the sentence, your hidden state, your mental summary, should encode the meaning of the whole sentence. And then you can use that final state to make a prediction, like what the next word should be, or whether the sentence expresses positive or negative sentiment. The concept of recurrent networks goes back to the 1980s, but the version that really made them practical was called the Long Short-Term Memory Network, or LSTM, invented by Sepp Hochreiter and Jürgen Schmidhuber in 1997. And the reason LSTMs were necessary is, you guessed it, the vanishing gradient problem, showing up again in a slightly different costume. In a standard recurrent network, when you try to back-propagate the error signal through many time steps, many words, the gradient shrinks exponentially, just like it did through many layers, so the network can't learn long-range dependencies. It forgets what it read at the beginning of a long sentence by the time it reaches the end. Hochreiter and Schmidhuber's solution was to add a memory cell, a special unit that could store information over long periods and selectively read, write, and erase that memory using learned gates. It's like giving your reader not just a running mental summary, but a notebook where they can write down important facts and refer back to them later. The gates control what gets written to the notebook, what gets read from it, and what gets erased. And because the memory cell has a direct connection through time, a kind of skip connection, actually, similar in spirit to what ResNet would later do for depth, the gradient can flow through the memory cell without vanishing, allowing the network to learn dependencies across hundreds of time steps. LSTMs became the workhorse of natural language processing throughout the 2000s. Google used them for machine translation. Apple used them in Siri. They powered speech recognition systems, text generation, sentiment analysis, basically anything involving sequences. And for a while, it seemed like LSTMs, combined with a clever mechanism called attention, that let the network focus on different parts of the input sequence when generating each part of the output, were going to be the architecture for language. But then, in 2017, a team at Google published a paper with one of the most understated yet consequential titles in the history of machine learning. It was called Attention is all you need. And it introduced something called the transformer. And the transformer changed everything. It didn't just improve on LSTMs, it replaced them. And to understand why, you need to understand what was actually limiting those earlier sequence models, even the good ones. See, LSTMs were powerful, no question. But they had a fundamental bottleneck built right into their design. They processed sequences one step at a time. Word by word, token by token, left to right. The hidden state at position 50 depended on the hidden state at position 49, which depended on 48, and so on, all the way back to the beginning. That sequential dependency meant two things. First, you couldn't easily parallelize the computation. You had to wait for each step to finish before you could compute the next one, which made training slow, especially on long sequences. And second, even with the memory cell and the gates and all those clever mechanisms, information still had to travel through a chain of steps to get from one end of a sentence to the other. The attention mechanism that had been bolted onto LSTMs helped with this. It let the decoder look directly at any part of the input when generating output. But the encoder itself was still sequential, still slow, still fundamentally a chain. The team behind the transformer paper, Ashish Vaswani, Noam Shazir, Nikki Parmar, Jakob Uskarit, Lion Jones, Aidan Gomez, Łukasz Kaiser, and Ilya Polosukin asked a beautifully simple question. What if you didn't need the recurrence at all? What if attention alone was enough to capture the relationships between all the words in a sequence without processing them one at a time? And here's what they came up with. Instead of feeding words through a chain, the transformer processes the entire sequence at once. Every word attends to every other word simultaneously. Think about that for a second. In an LSTM, if you want the word at position 1 to influence the processing of the word at position 100, that signal has to travel through 99 sequential steps. In a transformer, word 1 and word 100 can interact directly in a single operation. It's like the difference between passing a message down a long line of people, telephone game style, versus everyone being in the same room and being able to talk to anyone directly. The mechanism that makes this possible is called self-attention, and it's worth slowing down to really understand how it works, because it's the beating heart of essentially every major language model you've heard of since 2017, GPT, BERT, all of them. So, imagine you have a sentence. Let's say, the cat sat on the mat because it was tired. Now, as a human, you instantly know that it refers to the cat, not the mat. But how would a machine figure that out? In a self-attention layer, every word in the sentence creates three things: a query, a key, and a value. These are just vectors, lists of numbers, computed by multiplying the word's representation by three different learned weight matrices. You can think of it like this. The query is a question. What am I looking for? The key is a label. Here's what I contain. And the value is the actual content. Here's the information I'll share if you find me relevant. For each word, the model computes how well that word's query matches every other word's key. That match, that compatibility score, tells the model how much attention this word should pay to every other word. The scores get normalized using something called softmax, which just turns them into a set of weights that add up to 1, like probabilities, and then the output for each word is a weighted sum of all the values, where the weights are those attention scores. So when the model processes the word it, its query might match strongly with the key for cat, because through training, The model has learned that pronouns tend to refer back to nouns with certain properties, and weakly with mat, or on, or because. The result is that the representation of it gets infused with information about cat. The model has learned to resolve the reference, not through any explicit rule, but just through the patterns in the attention weights. And here's what's really clever. The transformer doesn't just do this once. It uses something called multi-head attention, where several different sets of query, key, and value matrices operate in parallel. Each head can learn to attend to different kinds of relationships. One head might learn syntactic relationships, subject-verb agreement, for instance. Another might learn semantic relationships, what concepts are related. Another might learn positional patterns. It's like having multiple independent readers, each highlighting different things in the same text, and then combining their highlights. Now, you might be thinking, if you process all words simultaneously, how does the model know what order they're in? In an LSTM, order is implicit because words are fed in sequentially. But in a transformer, since everything is processed at once, you need to explicitly tell the model about position. The original paper handled this with positional encodings. They added a unique pattern of numbers to each word's representation based on its position in the sequence. The specific pattern they used was based on sine and cosine waves of different frequencies, which is a delightfully elegant trick borrowed from signal processing. Different positions get different patterns, and the model can learn to use these patterns to understand word order. The full transformer architecture has an encoder and a decoder, each made of stacked layers. The encoder processes the input sequence using self-attention and feed-forward networks. The decoder generates the output sequence one token at a time, attending both to its own previously generated tokens and to the encoder's output through cross-attention. Each layer also includes residual connections, those skip connections from ResNet, showing up again, and layer normalization, which helps stabilize training. The whole thing is remarkably modular and clean, compared to the Baroque complexity of LSTM-based encoder-decoder models with attention bolted on, and the results were immediate and striking. On machine translation benchmarks, the transformer outperformed the best existing models while training significantly faster, because all that parallel processing meant you could fully exploit GPUs in a way that sequential LSTMs never could. The training time for state-of-the-art translation dropped from days to hours. But the real impact of the transformer wasn't just better translation. It was that this architecture turned out to be extraordinarily general, and the people who figured that out most dramatically were working on something that might seem, at first, almost too simple to be revolutionary. They were working on the next word prediction problem. Here's the idea. Take a massive amount of text, books, websites, articles, everything you can get your hands on. Feed it into a transformer and train it to predict the next word given all the previous words. That's it. That's the entire training objective. Given, the cat sat on the predict mat. Given to be or not to predict be. It sounds almost trivially simple, right? But think about what the model has to learn in order to get good at this task across billions of sentences. To predict the next word accurately, it needs to understand grammar, syntax, semantics, facts about the world, common sense reasoning, style, tone. Essentially, it needs to build a rich internal model of language and the world that language describes. This is the insight behind GPT, Generative Pre-trained Transformer, developed by OpenAI. The first version, GPT-1, was published in 2018 by Alec Radford and colleagues. It used only the decoder part of the transformer architecture, no encoder, because for next word prediction, you only need to attend to previous words, not to a separate input sequence. GPT-1 had 117 million parameters and was trained on a dataset of about 7,000 unpublished books. It showed something remarkable. After this pre-training on raw text, the model could be fine-tuned on specific tasks, sentiment analysis, question answering, textual entailment, with relatively small amounts of labeled data and achieve competitive results. The pre-training gave it a general understanding of language that transferred across tasks. But it was GPT-2, released in 2019, that really turned heads. GPT-2 had 1.5 billion parameters, about 13 times larger than GPT-1, and was trained on a much larger dataset scraped from the internet. And the striking finding was that GPT-2 could perform many tasks without any fine-tuning at all. You could just prompt it with a few examples of what you wanted, right there in the input text, and it would figure out the pattern and continue accordingly. This was called zero-shot or few-shot learning, and it suggested something profound. Scale itself, more parameters, more data, more compute, was unlocking capabilities that smaller models simply didn't have. OpenAI actually made the unusual decision to initially withhold the full GPT-2 model, citing concerns about potential misuse for generating fake news or spam. That decision was controversial. Some researchers argued it was more about publicity than genuine safety concerns. But it signaled that the field was starting to grapple with the implications of what it was building. These weren't just academic curiosities anymore. Meanwhile, on the other side of the transformer family tree, a team at Google, led by Jacob Devlin, was exploring a different approach. Instead of using just the decoder and training on next word prediction, they used the encoder part of the transformer and trained it on a different objective: masked language modeling. The idea was to take a sentence, randomly mask out some of the words, replace them with a blank, and train the model to predict what the missing words were. This forced the model to build representations that captured context from both directions, both the words before and after the blank. They called this model BERT, which stood for Bidirectional Encoder Representations from Transformers, and when they published it in October 2018, it swept the board on virtually every NLP benchmark. BERT became the foundation for Google's search engine improvements, and its influence on the field was enormous. Suddenly, the standard approach to almost any NLP problem was to start with a pre-trained transformer, either BERT style or GPT style, and fine-tune it for your specific task. And this is where something fascinating happened in the dynamics of the field. You had these two competing paradigms, the encoder-focused, bidirectional approach of BERT and the decoder-focused, autoregressive approach of GPT. And for a while, it wasn't clear which would win out. BERT was better at understanding tasks, things like classification and question answering, where you need to analyze a given text. GPT was better at generation tasks, producing fluent text. Researchers debated which approach was more fundamental, which would scale better, which captured more of what language really is. But then, GPT-3 arrived in 2020, and the debate shifted. GPT-3 had 175 billion parameters. Let that number sink in for a moment. From 117 million in GPT-1 to 1.5 billion in GPT-2 to 175 billion in GPT-3. Each jump was roughly an order of magnitude or more. And GPT-3 was trained on a staggering amount of text, hundreds of billions of words drawn from Common Crawl, web text, books, and Wikipedia. The training compute alone was estimated to cost several $1,000,000. And what emerged from all that scale was something that genuinely surprised people, even people who had been working in the field for decades. GPT-3 could do things that nobody had explicitly trained it to do. You could give it a few examples of translating English to French, and it would translate. You could give it a few examples of simple arithmetic, and it would do arithmetic. Not perfectly, but far better than you'd expect from a system that had never been taught math. You could ask it to write code, compose poetry, summarize legal documents, explain scientific concepts. It wasn't perfect at any of these things, but the breadth was astonishing. The model had learned something that looked, from the outside, like a general understanding of language and reasoning, just from predicting the next word over and over and over again on an enormous pile of text. This raised a question that the field is still wrestling with today, a question that touches on philosophy as much as engineering. What exactly has the model learned? Is it really understanding language, or is it doing something more like very sophisticated pattern matching? When GPT-3 answers a question correctly, does it know the answer in any meaningful sense, or has it just learned statistical regularities in its training data that happen to produce the right output? There's no consensus on this, and honestly, the answer might depend on what you mean by understanding in the first place. But what's undeniable is the practical impact. These models work. They produce outputs that are useful, coherent, and often remarkably insightful. And they get better as they get bigger, in ways that follow surprisingly predictable patterns. Those patterns, in fact, became a subject of study in their own right. Researchers at OpenAI, Google, and DeepMind began documenting what they called scaling laws, empirical relationships between model size, dataset size, compute budget, and performance. And what they found was that performance improved smoothly and predictably as you increased these factors, following power law curves. Double the parameters, and you get a predictable improvement. Double the training data, another predictable improvement. This meant you could, to some extent, forecast how good a model would be before you even trained it, just by knowing how big it was going to be and how much data you were going to feed it. It also meant that the recipe for better models was, in a sense, embarrassingly simple. Make them bigger, feed them more data, and throw more compute at them. But that simplicity is deceptive because the engineering challenges of actually doing this at scale are enormous, genuinely staggering when you start to dig into what it actually takes to train one of these things. Because it's one thing to say, just make the model bigger, and it's another thing entirely to figure out how to fit a model with hundreds of billions of parameters across dozens or even thousands of GPUs. Keep all of them synchronized. Feed them data fast enough that they're not sitting idle. Manage the heat. Manage the memory. Manage the sheer electricity bill. And do all of this for weeks or months without a single hardware failure crashing the whole run. Training GPT-3, for instance, required something on the order of 3.14 times 10 to the 23rd floating point operations. That's a number so large it's basically meaningless to the human brain, so let me put it differently. If you had a single modern GPU and tried to train GPT-3 on it, it would take you roughly 355 years. Not a typo. 3.5 centuries. So obviously, you don't use one GPU. You use thousands of them, working in parallel, and you figure out clever ways to split the model and the data across all of them so that the whole thing finishes in a reasonable time frame, weeks, maybe a couple of months. But coordinating thousands of GPUs is itself a massive engineering problem. You've got to think about communication bandwidth between the machines, because every few milliseconds they need to share gradient information with each other, and if that communication is slow, everything bottlenecks. You've got to think about what happens when one GPU in the cluster fails, and with thousands of them running for weeks, failures are not a possibility, they're a certainty. You need checkpointing, where you periodically save the state of the entire training run so you can restart from a recent point if something goes wrong. You need mixed precision training, where you use lower precision numbers, 16-bit floating point instead of 32-bit, to save memory and speed things up. But you have to be careful because lower precision means more rounding errors, and those can accumulate and destabilize the whole training process if you're not managing them properly. And then there's the data. GPT-3 was trained on roughly 300 billion tokens of text, drawn from a filtered version of Common Crawl, which is basically a snapshot of the internet, plus books, Wikipedia, and other curated sources. But you can't just dump raw internet text into a model and expect good results. You have to clean it, deduplicate it, filter out garbage, handle the fact that some sources are much higher quality than others. The data pipeline itself is a major engineering effort, and the choices you make about what data to include and what to exclude have profound effects on what the model learns, what biases it picks up, what it's good at, and what it's terrible at. Here's the thing that I think is really worth sitting with for a moment, though. All of this, the distributed computing, the data cleaning, the mixed precision arithmetic, the checkpointing, all of it is in service of doing one thing. The same thing we've been talking about since the very beginning of this whole story. Adjusting weights to reduce a loss function. That's it. The fundamental learning algorithm is still, at its core, back-propagation. Compute a prediction, compare it to what you wanted, calculate the gradient of the error with respect to every parameter, and nudge each parameter a tiny bit in the direction that reduces the error. The same idea Rumelhart, Hinton, and Williams published in 1986. The same chain rule from calculus. It's just happening now across 175 billion parameters instead of a few hundred, and it's happening on hardware that would have been unimaginable in 1986, but the mathematical bones are the same. There's something kind of beautiful about that continuity. But the scaling story doesn't stop at GPT-3. Not even close. Because once the field had established that bigger models trained on more data reliably got better, a kind of arms race began. And this is where the story starts to involve not just researchers in labs, but entire corporations, billions of dollars, geopolitics, and energy infrastructure. Google had been working on their own large language models. They'd published the Transformer paper in the first place, after all. And in 2022, they had a model called Palm, with 540 billion parameters. DeepMind, also owned by Alphabet, was doing their own work with models like Chinchilla, which actually pushed back on the just make it bigger narrative in an interesting way. The Chinchilla paper, published in 2022 by Jordan Hoffman and colleagues, argued that many existing large models were actually undertrained. They had too many parameters relative to the amount of data they'd been trained on. The optimal balance, they found, was to scale parameters and training data roughly equally. A model with 70 billion parameters trained on 1.4 trillion tokens could outperform a 175 billion parameter model trained on 300 billion tokens. This was a genuinely important finding because it suggested that the field had been somewhat wasteful, building models that were bigger than they needed to be, when what they really needed was more data and more training time for smaller models. So you had this fascinating tension. On one hand, the raw scaling approach, just make everything bigger. On the other hand, a more nuanced view. Scale smartly, find the right balance between model size and data. And in practice, both insights fed into the next generation of models. When OpenAI released GPT-4 in March 2023, they were notably secretive about its architecture and size. They didn't publish the parameter count, the training data details, or even the basic architectural choices. This was a dramatic shift from the earlier days of open publication, and it reflected the fact that large language models had become commercially valuable in a way that academic research traditionally isn't. GPT-4 was a product, not just a paper, and its capabilities were striking. It could pass the bar exam. It could score in the top percentiles on the SAT. It could write code, analyze images. It was multimodal, meaning it could process both text and images, and it could engage in extended, nuanced reasoning that genuinely surprised people who interacted with it. Now, around this same time, something else was happening that's worth talking about, because it changed the dynamics of the whole field. Meta, Facebook's parent company, made the decision to release their large language model, LLaMA, with its weights available to researchers. The first version came out in February 2023, and it was significant not because it was the biggest or best model, but because it was open. Within weeks, the research community had taken those weights and started fine-tuning, modifying, and experimenting with them in ways that would have been impossible with closed models like GPT-4. A version called Alpaca, created at Stanford, showed that you could fine-tune LLaMA on a relatively small set of high-quality instruction-following examples and get surprisingly good results for a cost of under $600. This blew the doors open. Suddenly, the idea that you needed billions of dollars and a massive data center to work with large language models was being challenged. Not entirely overturned, the biggest, most capable models still required enormous resources to train from scratch. But the fine-tuning and adaptation of existing models became accessible to a much wider community. And this brings up a concept that became really important in this era: the distinction between pre-training and fine-tuning. Pre-training is the expensive part. That's where you take a randomly initialized model and train it on a vast corpus of text, teaching it the statistical structure of language. This is where the model learns grammar, facts, reasoning patterns, style, everything it picks up from processing hundreds of billions or trillions of tokens. Fine-tuning is what comes after. You take a pre-trained model and train it further on a smaller, more specific dataset, often with human feedback, to make it behave in ways that are more useful, more aligned with what users actually want. This is where a raw language model that can complete any text gets shaped into something that can follow instructions, answer questions helpfully, and avoid producing harmful or misleading content. The fine-tuning step is where a technique called reinforcement learning from human feedback, RLHF, enters the picture, and it's worth understanding because it represents a genuinely different kind of learning from what we've been talking about. Up to this point, the learning signal has been relatively straightforward. Predict the next word and adjust your weights to get better at it. But RLHF adds a layer on top of that. Here's how it works. You start with your pre-trained model, and you have it generate multiple responses to the same prompt. Then human evaluators rank those responses. This one is better than that one. This one is more helpful. This one is less harmful. You use those human rankings to train a separate model called a reward model, which learns to predict how a human would rate any given response. And then, you use that reward model as a signal to further train the language model using reinforcement learning techniques, specifically an algorithm called Proximal Policy Optimization, or PPO. The language model generates responses, the reward model scores them, and the language model is updated to produce responses that score higher. Think about what that means. The model is no longer just learning to predict text. It's learning to produce text that humans prefer. And that's a subtle but profound shift, because human preferences encode all sorts of things: helpfulness, accuracy, safety, tone, the avoidance of certain kinds of content. It's a way of injecting human values, however imperfectly, into the learning process. And it works remarkably well, which is why the ChatGPT that was released in November 2022 felt so different from raw GPT-3. ChatGPT was built on GPT 3.5, an improved version of GPT-3, but the real magic was in the RLHF fine-tuning. It was the same underlying architecture, the same basic pre-training approach, but shaped by human feedback into something that felt like a conversation partner rather than an autocomplete engine. The response to ChatGPT was unlike anything the AI field had seen. It reached 100 million users in 2 months, faster than any application in history at that point, and it triggered a wave of investment, competition, and public attention that transformed the landscape almost overnight. Google rushed to release Bard, their own conversational AI. Anthropic, founded by former OpenAI researchers Dario and Daniela Amodei, released Claude. Microsoft invested $13 billion in OpenAI and began integrating GPT-4 into Bing, Office, and essentially every product they had. The amount of money flowing into AI infrastructure, data centers, GPU manufacturing, energy supply, reached levels that would have seemed absurd just a few years earlier. And here's what's fascinating about all of this from an engineering perspective. The core architecture, the transformer, hadn't fundamentally changed since 2017. The core training algorithm, backpropagation with gradient descent, hadn't fundamentally changed since 1986. What had changed was scale, data, and the clever addition of techniques like RLHF to shape model behavior. The breakthroughs were real and dramatic, but they were built on foundations that had been laid decades earlier by people who often didn't live to see their ideas vindicated at this scale. But scale alone doesn't explain everything that was happening. Because as these models got bigger and were trained on more data, they started exhibiting behaviors that nobody had explicitly programmed or even expected. Researchers began calling these emergent capabilities, abilities that seemed to appear suddenly as models crossed certain size thresholds. A model with 10 billion parameters might be terrible at, say, multi-step arithmetic, and then a model with 100 billion parameters might be surprisingly decent at it, without anyone having changed the training objective or added arithmetic-specific training data. It was as if certain capabilities had a critical mass. Below a certain scale, they didn't exist at all, and above it, they appeared almost fully formed. And that's a strange thing to wrap your head around, because it cuts against how we normally think about learning. Usually, you expect gradual improvement, a little more training, a little better performance, a smooth upward curve. But what researchers were observing with large language models was something more like a phase transition. Think about water. You can cool water down from room temperature, and it stays liquid the whole way. 20 degrees, 15, 10, 5, 1, still liquid. And then you hit 0, and suddenly it's ice. The underlying physics didn't change. The molecules are the same. But at a critical threshold, the behavior of the whole system shifts dramatically. That's roughly the analogy people were reaching for when they talked about emergent capabilities in large language models. A model with a few billion parameters might produce garbled nonsense when you ask it to reason through a logic puzzle. You scale it up by a factor of 10, and it still produces garbled nonsense, maybe slightly better garbled nonsense. And then you scale it up by another factor of 10, and suddenly it can do the puzzle. Not perfectly, not every time, but the capability is clearly there in a way it simply wasn't before. Now, here's the thing, and this is important to be honest about. The exact nature of emergence in these models is genuinely debated. A paper from researchers at Stanford in 2022 documented a whole list of these emergent abilities, things like chain of thought reasoning, translation between languages the model had barely seen, even basic code generation. The paper was striking because it showed these sharp jumps in performance graphs. Flat, 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 then suddenly up. But other researchers, notably a group from Stanford's own computer science department, in a later 2023 paper, pushed back and argued that some of these apparent phase transitions might be artifacts of how you measure performance. If you use a very strict metric, like the answer is either exactly right or it's wrong, no partial credit, then of course you'll see sharp jumps. Switch to a more continuous metric that gives partial credit, and the improvement curve might actually be smoother than it looked. The capability was building gradually all along. It's just that your yardstick was too coarse to detect it. So the truth is probably somewhere in the middle. Some capabilities really do seem to require a minimum scale before they click into place, while others are improving gradually and we just weren't measuring them carefully enough. But either way, the practical effect was undeniable. Models at the scale of GPT-4 could do things that models a fraction of their size simply could not do in any useful way. And this created a genuine puzzle for the field, because it meant you couldn't always predict what a model would be capable of just by looking at smaller versions. You had to actually build the big thing and see what happened. And this unpredictability is part of what made the conversation around AI safety and alignment suddenly feel so urgent. Because if you can't predict what capabilities will emerge at the next scale, how do you ensure that the model behaves the way you want? RLHF, that technique we talked about where human feedback shapes the model's outputs, helps a lot. It's the reason ChatGPT gives you a helpful, polite response instead of something toxic or dangerous. But RLHF is essentially a behavioral veneer. It shapes how the model presents its outputs. It doesn't change the underlying knowledge or capabilities baked into the weights during pre-training. The model still knows how to produce harmful content. It's just been trained to decline when asked. And researchers found, pretty quickly, that you could often get around those guardrails with clever prompting, what people started calling jailbreaks. This is where the story connects to a much deeper question that had been simmering in the AI safety community for years, really since before these models became mainstream. People like Stuart Russell at Berkeley and organizations like the Machine Intelligence Research Institute had been arguing for a long time that alignment, making sure an AI system's goals and behaviors actually match what humans want, was going to be one of the most important engineering challenges of the century. For a long time, those warnings felt abstract, almost philosophical. But when you had a system that 100 million people were using every day, a system that could write convincing text on any topic, generate code, help with medical questions, assist with legal documents, suddenly alignment wasn't abstract anymore. It was an engineering problem with real stakes, happening right now. Let's talk about what alignment actually looks like in practice, because it's more nuanced than it might seem. The goal isn't just make the model say nice things. It's about making the model helpful, honest, and harmless. A framework that Anthropic in particular has articulated clearly, and those three goals can actually be in tension with each other. Helpful means the model should answer your question as thoroughly and accurately as possible. Harmless means it shouldn't help you do dangerous things. But what if you ask a chemistry question that has both legitimate educational value and potential for misuse? Being maximally helpful might conflict with being maximally harmless. The model has to navigate these trade-offs, and the way it navigates them is shaped by RLHF and by additional techniques that have been developed since. One of those techniques is constitutional AI, which Anthropic introduced in 2022. The idea is elegant. Instead of relying entirely on human raters to rank outputs, which is expensive, slow, and subject to all the biases and inconsistencies of individual human judgment, you give the model a set of principles, a constitution, and then have it critique and revise its own outputs according to those principles. So the model generates a response. Then a separate pass evaluates that response against the Constitution. Is it helpful? Is it honest? Could it cause harm? And produces a revised version. You can then use those self-generated revisions as training data for reinforcement learning, reducing the need for massive amounts of human feedback. It's still not perfect, but it's a clever way to scale alignment training. And then there's the technique that arguably changed the game for what these models could actually do in terms of reasoning: chain of thought prompting. This one is beautiful in its simplicity. Researchers at Google Brain, led by Jason Wei, published a paper in early 2022 showing that if you simply prompted a large language model to think step by step, literally just including the words, "Let's think step by step" in the prompt, or showing the model an example where the reasoning was laid out explicitly, the model's performance on math problems, logic puzzles, and multi-step reasoning tasks improved dramatically. Not because the model's weights changed, not because it was retrained, just because the prompt encouraged it to generate intermediate reasoning steps, and those intermediate steps kept the computation on track. Think about what that means for a second. The model already had the capability to reason through these problems. It just needed to be asked in the right way. It's like having a student who can solve a word problem if you tell them to show their work, but gets the wrong answer if you just ask for the final number. The knowledge is there, the capability is there, but the format of the output matters because each token the model generates becomes part of the context for the next token. When it writes out, "First, let's figure out how many apples are left after Tuesday," that text is now part of the input for generating the next piece. The model is essentially thinking on paper, or thinking on tokens if you want to be precise about it. This insight led to a whole family of techniques: chain of thought prompting, tree of thought, where the model explores multiple reasoning paths and evaluates which one is most promising, self-consistency, where you generate multiple chain of thought solutions and take a majority vote on the final answer. And eventually, it led to models that were explicitly trained to produce long chains of reasoning before giving a final answer. Models like OpenAI's O1 series, released in late 2024, which were specifically optimized for extended reasoning. The model would generate what amounted to an internal monologue, sometimes hundreds of tokens long, working through a problem before committing to an answer. And the results on math, science, and coding benchmarks were striking. But here's what's really interesting about all of this. Every one of these techniques, RLHF, constitutional AI, chain of thought prompting, reasoning optimized training, they're all operating on top of the same fundamental architecture. It's still a transformer. It's still trained with backpropagation. The attention mechanism is still doing the same thing Vaswani and his colleagues described in 2017. What's changed is how we prepare the data, how we prompt the model, how we fine-tune its behavior after pre-training. The innovations are happening at the layer above the architecture, in training methodology, in data curation, in the interface between human intent and model behavior. And that brings us to something that's been quietly reshaping the field in a way that doesn't always make headlines, but might end up being just as important as any of the breakthroughs we've talked about. Because while the biggest labs were racing to build ever larger models, a parallel movement was asking a different question entirely. How small can you make these models while keeping them useful? The answer turns out to be surprisingly small. And the techniques that make that possible are fascinating in their own right, because they reveal something deep about what these networks actually learn and what's redundant. Researchers found that you could take a model with 70 billion parameters and, through a process called quantization, reduce the precision of each parameter. Instead of storing each weight as a 32-bit floating point number, you store it as 8 bits or 4 bits, or, in some aggressive experiments, even fewer. And the model would still work remarkably well. Not perfectly. You lose some quality at the margins. But the practical difference between a 16-bit model and a 4-bit quantized version of the same model was often shockingly small, while the memory footprint dropped by a factor of 4 or more. And quantization was just the beginning. There was pruning, where you identify and remove weights that contribute very little to the model's outputs, essentially trimming the network down to its essential structure. There was knowledge distillation, where you train a smaller model to mimic the behavior of a larger one, transferring the big model's capabilities into a more compact form. And there was a technique called LoRa, low-rank adaptation, introduced by researchers at Microsoft in 2021, which offered a way to fine-tune a large model for a specific task by only training a tiny number of additional parameters, leaving the vast majority of the original weights frozen. LoRa made it possible for someone with a single consumer GPU to customize a model that would normally require a whole data center to train from scratch. These efficiency techniques mattered enormously because they democratized access. When Meta released the Llama weights, and when quantization tools made it possible to run those models on a laptop, the entire dynamic of the field shifted. Suddenly, it wasn't just Google and OpenAI and a handful of deep-pocketed labs that could work with powerful language models. Graduate students could do it. Hobbyists could do it. Small companies in countries without massive GPU clusters could do it. An open-source ecosystem exploded. Projects like llama.cpp, which let you run llama models in pure C++ on a MacBook, no GPU required. Fine-tuned variants proliferated on platforms like Hugging Face, each one optimized for a different use case, a different language, a different domain. And this is where the story of neural networks starts to intersect with something much bigger. Questions about who controls this technology, who benefits from it, who gets to decide how it's used, because the same model that can help a doctor in rural Kenya triage patients can also generate convincing disinformation at scale. The same architecture that powers a brilliant coding assistant can write malware. The dual-use nature of these systems isn't a bug or an oversight. It's inherent in what they are. They're general-purpose text generators. They don't know what they're being used for. They just predict the next token. And so, by 2024, the field found itself in a genuinely unprecedented position. The technology was advancing faster than the institutions meant to govern it could keep up. The European Union passed the AI Act, the first comprehensive regulatory framework for artificial intelligence, categorizing AI systems by risk level and imposing requirements on high-risk applications. In the United States, the approach was more fragmented: executive orders, voluntary commitments from major labs, congressional hearings that often revealed how little legislators understood about the technology they were trying to regulate. China pursued its own path, with tight control over model deployment domestically and aggressive investment in indigenous AI capabilities. But underneath all the policy debates and corporate strategy and geopolitical maneuvering, the engineering reality remained what it had always been. These are mathematical systems. They learn by adjusting weights to minimize a loss function. They process information through layers of simple operations, matrix multiplications, nonlinear activations, attention mechanisms, repeated billions of times. And the fact that such simple ingredients can produce behavior that looks like understanding, that looks like reasoning, that can pass medical licensing exams and write poetry and debug code, that fact is still, honestly, a little bit mysterious. Not in a mystical way, in an engineering way. Because we built these systems, we know exactly what every component does, and yet the emergent behavior of the whole system exceeds what we can fully explain from the parts. This gap between what we can build and what we can explain has given rise to an entire subfield called mechanistic interpretability, and the people working on it are trying to do something genuinely ambitious. They're trying to reverse engineer the algorithms that neural networks discover during training. Not just knowing that the network works, but understanding how it works at the level of individual neurons and circuits. And some of what they've found is genuinely surprising, because the circuits these networks learn aren't random tangles of connections. They're structured, they're interpretable, and in some cases, they look a lot like algorithms a human engineer might have designed on purpose. One of the landmark pieces of work in this space came from Chris Olah and his collaborators, first at Google Brain and later at Anthropic. Olah had been thinking about neural network interpretability for years, publishing beautiful interactive articles that tried to visualize what individual neurons in image classifiers were detecting. And what he and his team found, when they looked carefully at the internal structure of trained networks, was that neurons organized themselves into meaningful circuits. In a vision model, for example, you could find individual neurons that detected edges at specific angles. Those edge-detecting neurons fed into other neurons that combined edges into curves, curves combined into shapes, shapes combined into textures and patterns. And higher up in the network, you'd find neurons that responded to specific objects: a car, a dog's ear, a human eye. This wasn't programmed. Nobody told the network to build an edge detector in layer 1 and a curve detector in layer 2. The network discovered this hierarchy entirely through backpropagation, through the slow adjustment of weights to minimize classification error on millions of training images. And here's what's really fascinating about that. This hierarchy, edges to curves to shapes to objects, mirrors the hierarchical processing that neuroscientists have observed in the primate visual cortex. The brain's visual system processes information through a series of stages, from simple features to complex ones, and neural networks trained on image classification independently converge on a remarkably similar architecture. Nobody designed that correspondence. It emerged from the optimization process itself, from the pressure to classify images accurately. But Olah's team went further than just finding individual feature detectors. They mapped out how neurons connected to each other, tracing the circuits that implemented specific computations. They found what they called induction heads in language models, small circuits that implement a simple but powerful algorithm. If you've seen pattern A followed by pattern B earlier in the text, and then you see pattern A again, predict that B comes next. That's a basic form of in-context learning, and the network builds it from scratch during training. The circuit has specific, identifiable components. Attention heads that look backward for previous occurrences of the current token, and other heads that copy the token that followed those previous occurrences into the prediction. It's an algorithm. A real, legible algorithm, implemented in the weights and attention patterns of the network. In 2023 and 2024, this line of work accelerated dramatically. Anthropic published research on what they called superposition, the idea that neural networks represent far more features than they have neurons, by encoding multiple features in overlapping patterns of activation across groups of neurons. Think of it like this. Imagine you have a room with 1,000 light switches, and each switch can be on or off. You might think you can only represent 1,000 different things, one per switch. But if you use combinations of switches, patterns where switch 17 and switch 403 and switch 812 are all on together to represent one concept, then you can represent an astronomically larger number of things. Neural networks seem to do something like this, encoding thousands or even millions of distinct features in the activation patterns of a much smaller number of neurons. This makes interpretability harder because you can't just look at one neuron and ask what it does. Its meaning depends on the context of what other neurons are doing simultaneously. But it also explains why neural networks can be so efficient, why a model with a few billion parameters can seem to know so much. The information is compressed, distributed, encoded in these overlapping patterns. To crack this open, researchers developed techniques like sparse autoencoders, essentially training a second neural network to decompose the activations of the first network into a much larger set of interpretable features, most of which are inactive at any given time. When Anthropic applied this technique to Claude, one of their language models, they found thousands of clearly interpretable features, concepts like the Golden Gate Bridge, or code written in Python, or expressions of uncertainty, each represented by a specific direction in the model's activation space. And when they artificially amplified or suppressed these features, the model's behavior changed in predictable ways. Amplify the Golden Gate Bridge feature, and the model starts mentioning the Golden Gate Bridge in contexts where it normally wouldn't. It's a little eerie, honestly, like finding the specific knob in someone's brain that controls how much they think about a particular landmark. Now, this work is still in its early stages. We can identify individual features and small circuits, but we're very far from having a complete map of what a large language model knows and how it processes information. The gap between understanding a few circuits and understanding the whole system is enormous, like the difference between identifying a few genes and understanding the entire human genome's interaction with the body. But the direction is promising, and it matters for reasons that go well beyond scientific curiosity. Because here's why mechanistic interpretability is so important. If we can actually understand what's happening inside these models, not just observing their behavior from the outside, but reading their internal computations, then we have a much better shot at building AI systems we can genuinely trust. Instead of just training a model and hoping it behaves well, we could inspect its internal representations and verify that it's actually doing what we think it's doing. We could detect deception if a model ever learned to behave well during evaluation while harboring different objectives internally. we could identify dangerous capabilities before they manifest in behavior. This is the dream anyway. The engineering reality is that we're still a long way from being able to do this reliably at scale. And that tension between the pace of capability development and the pace of safety research is probably the defining tension of this moment in the history of neural networks. The capabilities keep advancing. New models keep getting more powerful. And the understanding of how and why they work keeps lagging behind. But let's step back from that tension for a moment and think about something else. Think about the arc of the story we've been following tonight, because it really is a remarkable arc when you lay it all out. It starts in 1943 with Warren McCulloch and Walter Pitts writing a paper about simplified mathematical neurons, trying to understand how logic could emerge from biology. It moves through Frank Rosenblatt's Perceptron in 1958, that burst of optimism, the New York Times headline about a machine that could learn. Then the crash, Minsky and Papert's book in 1969, showing the perceptron's limitations, and the first AI winter that followed. Years in the wilderness. Funding dried up. Researchers who believed in neural networks had to work on other things or pursue their ideas quietly, almost in secret. Then, back-propagation, rediscovered and popularized in 1986 by Rumelhart, Hinton, and Williams, showing that you could train networks with multiple layers by propagating error signals backward through the network. That insight, which is really just the chain rule from calculus, applied systematically, unlocked everything that followed. But it took decades for the full potential to become apparent, because the computers weren't powerful enough yet, and the datasets weren't large enough, and there were technical obstacles like the vanishing gradient problem that made deep networks hard to train. Yann LeCun's convolutional networks in the late 1980s and 1990s showed what was possible for specific tasks like handwriting recognition. But the broader AI community had largely moved on to other approaches: support vector machines, random forests, methods that came with theoretical guarantees and didn't require the massive computational resources that neural networks seem to need. And then Hinton again, in 2006, showing that deep networks could be trained if you were clever about initialization. And the ReLU activation function, such a simple change, just replacing a curved function with a kinked line that turned out to solve the vanishing gradient problem. And GPUs, graphics cards designed for video games, repurposed for matrix multiplication, providing the computational horsepower that neural networks had always needed, but never had. AlexNet in 2012. That moment when a deep neural network crushed the competition in image recognition so decisively that the entire field pivoted almost overnight. Then the rapid succession of advances: deeper networks, batch normalization, residual connections, recurrent networks for sequences, LSTMs, attention mechanisms, each one solving a specific engineering problem, each one building on what came before. And then the transformer in 2017, which simplified everything by showing that you didn't need recurrence at all, just attention, applied in parallel across the entire input. That architecture, combined with massive scale, gave us BERT and GPT, and all the large language models that followed, the scaling laws that showed performance improving predictably with more data, more parameters, more compute, the emergence of capabilities that nobody explicitly trained for, and RLHF, that technique for fine-tuning models to be helpful and harmless, which turned a text prediction engine into something you could actually have a conversation with. Think about what that arc represents. It's 80 years of work, 80 years of people, mathematicians, neuroscientists, computer scientists, engineers, chipping away at the same fundamental question. Can machines learn? And the answer, it turns out, is yes, but not in the way anyone originally imagined. Not through handcrafted rules or explicit programming or symbolic logic. Through something much simpler and much stranger. Through optimization. Through adjusting millions and then billions of numerical weights, a tiny amount at a time, guided by nothing more than a signal that says how wrong you were on this particular example. The whole thing runs on calculus and linear algebra, derivatives and matrix multiplications, ideas that would have been familiar to mathematicians in the 19th century. And yet, the behavior that emerges from these simple operations, when scaled up sufficiently, is something that no one in the 19th century, or the 20th century for that matter, could have predicted. That's the thing about engineering that I find endlessly fascinating. You start with principles you understand completely. You know exactly how a transistor works, exactly how matrix multiplication works, exactly how gradient descent works. There's no mystery in any individual component. But when you combine enough components, when the system becomes sufficiently complex, something happens that transcends your understanding of the parts. The whole becomes not just greater than the sum of its parts, but different in kind, and you're left standing there, looking at something you built with your own hands, from pieces you understand perfectly, and you can't fully explain what it's doing or why it works as well as it does. That's where we are right now with neural networks. We built them. We know every equation, every algorithm, every training procedure. And yet, they surprise us. They write things we didn't expect. They solve problems we didn't think they could solve. They fail in ways we didn't anticipate. They are, in a very real sense, the most complex artifacts that human beings have ever created. Not because any individual piece is complicated, but because the interactions between billions of simple pieces create something that defies easy analysis. And the story isn't over. It's not even close to over. The people working on this, the researchers at universities and labs around the world, the engineers building the infrastructure, the people working on alignment and interpretability and safety, they're writing the next chapters right now. Some of them are probably awake at this very moment, staring at training curves on their monitors, tweaking hyperparameters, arguing about architecture, choices, debugging code at 2 a.m. because they can't stop thinking about a problem. That's how engineering has always worked. One person figures out a piece. Someone else figures out another piece. Someone combines them in a way nobody expected. And slowly, unevenly, with plenty of wrong turns and dead ends and moments of despair, the understanding deepens and the capabilities grow. So as you're lying there, maybe drifting off, maybe already half asleep, here's what I'd leave you with. Everything you heard tonight, the McCulloch-Pitts neuron, the perceptron, back-propagation, convolutional networks, the transformer, attention mechanisms, all of it. It all comes back to one simple, beautiful idea. A system that adjusts itself, a little bit at a time, to get less wrong. That's it. That's the whole secret. You start with random weights. You make a prediction. You measure how wrong you were, and you nudge the weights in the direction that would have made you a little less wrong. And you do that billions of times. And somehow, from that process, something emerges that can translate languages and write stories and diagnose diseases and fold proteins and carry on conversations that feel, at least sometimes, like talking to someone who understands, its gradient descent all the way down, and the fact that something so simple can give rise to something so complex. That might be the most interesting thing about it. Not the fancy architectures, or the massive compute clusters, or the billions of dollars in investment. Just the quiet, relentless process of getting a little bit less wrong, one step at a time. That's a good thought to fall asleep to, I think. The idea that learning, real learning, whether in a machine or in a brain, is just the patient accumulation of small corrections. No single step is dramatic. No single weight update changes everything. But over time, over millions and billions of tiny adjustments, something remarkable takes shape. Something that didn't exist before. Something that surprises even the people who built it. So let that settle in. Let the details blur if they want to. The names and dates and equations, they'll be there if you want to revisit them. For now, just hold on to that one idea. Learning is adjustment. Understanding emerges from repetition, and the most complex things in the world are built from the simplest ingredients, given enough time and enough patience, and enough willingness to be wrong along the way. That's true for neural networks, and honestly, it's true for most things worth building. Good night.